people logged in. So it's a great pleasure. First of all, I'd like to welcome everyone on behalf of the MateriAlZ um, seminar series. Uh, so Kumar Ankit, Christina Burkle, Erika Corral, and I, Krishna Muralidharan at the University of Arizona, we've come together and organized this seminar series, which is started in September and goes all the way till end of April. And we have a terrific lineup. But one of the stars in our lineup is Donald Godfrey, who's going to be our seminar speaker today. And I mean, I don't want to. I mean, most of you already know Don by now. He's a doyen in the field of additive manufacturing, extremely well known, lots of patents, lots of established a lot of relationships with other countries, established AM facilities in lots of other countries too. Currently, he's a senior fellow at SLM Solutions, and for people who don't know SLM, they are one of the biggest metal additive manufacturing equipment companies. And he's done a lot of service in the field of additive. He's also co-authored the book Additive Manufacturing of Metals, the technology materials design, which Springer, I guess, published it. So again, this talk is wide-ranging. It's going to cater to the people who know about additive, who don't know about additive. It's going to give you a nice overview of where the field is headed, and from a workforce development point of view, which is very important, and which is why people like us at the University of Arizona and Arizona State, we want to train the next generation of workforce, and they need to be closely aligned with the industry expectations as well as be critical thinkers and domain experts. And Don's going to also talk about those areas, like how people can prepare themselves to enter the workforce, especially in the field of additive. And the floor is yours, Don. Thanks a lot.
Oh, thank you so very much. Thank you for inviting SLM to be a part of this excellent opportunity. Two major universities in the Pac-12 and on the West Coast collaborating together to promote additive manufacturing and it's just an honor really to be a part of this. Hopefully we can get our Microsoft Teams software to work and you still see the screen, correct? I hope.
Yes.
Okay, good.
Yes.
All right, so what I want to do in this 45 minutes is give you a brief explanation of who SLM is. I want to explain and compare additive to other technologies. We're going to talk a little bit about case studies. We're going to talk a little bit about economics and what are the real barriers to accepting technology, and then some career opportunities. I recently was talking to some college students in Mexico, and most of their questions really was focusing on that last bullet, and it's very important. And so we're going to take time, since we're talking to universities, to address that topic right there. So SLM and the history of laser powder bed fusion. So just get this out of the way real quick. We'll do the 20-second sales pitch. SLM is a company out of Lübeck, Germany. I would say 95% of all metal-oriented printing technology originates out of Germany, as compared to polymers, which originates out of the United States of America. It's kind of interesting how that broke out that way. But in Sweden, you have the RCAM electron beam technology. But with regard to laser, it's definitely Germany. You have Concept Laser out of Germany. You have EOS out of Germany, Trumpf out of Germany, SLM out of Germany. And these companies dominate the global market, really. And SLM is located in Lübeck, which if you're student of history, Lübeck is a town that dates all the way back to the 14th century. If you go back there, if you ever visit, it's a United Nations World Heritage Site. It was not destroyed in World War II. It's called the City of Towers. There are churches there that are literally 800 years old, and it's a site for. When I was there last, it was a European pipe organ festival. These pipe organists go from city to city to city, so they played in the churches of Lübeck. You sit in the pews and the headrest hits you about where your shoulders are, because 200 years ago people just weren't as tall as we are. The big blue space up here at the top is the Baltic Sea. It literally is a Baltic region of Europe. We have subsidiaries in China, France, India, Italy, Russia, Singapore, and in the United States, we are in Wixom, Michigan, which is just about 20 minutes from downtown Detroit. And then we have distribution partners around the world. Real quickly, these are the 4 machines that we offer right now. We're coming out with a new one, an additional one. So 125 millimeters cubed is the build space. You see a lot of these 125 machines in universities around the world. The 280 and the 500 are the production facilities, production machines. And then the 800 is definitely a production machine, where it's 500 millimeters by 280 millimeters by 850 millimeters in the Z. All right, so that's the pitch. When we talk about additive manufacturing, we talk about not only just lasers and printing of metal, but the manufacturing and the distribution of metal is a technology that could be discussed for. It could be a college class in and of its own. And in fact, there are a lot of classes that focus on the metallurgy of powder manufacturing. And so let's just talk a little bit about this. When you compare manufacturing technologies, you have castings, you have forgings, you have machining, and we also have additive manufacturing. So castings has been around for thousands and thousands of years, where even the Romans used it a great deal and brought in the Bronze Age and the Iron Age, where they poured into sand. And believe it or not, sand casting is still a very, very much a technology used in automotive and aviation today. And then you take that casting and you heat it, and you can forge it either in a closed die or an open die to get you a shape that's near net. And then you would machine it, right? And from a purely just a physics standpoint, this is called subtractive manufacturing, because you are removing metal from a 3D shape. It could be a square, it could be a cube, it could be a cylinder like this picture, but you are subtracting. And we don't say, I'm going to go out into the shop floor and do some subtractive manufacturing. Nobody says that, right? Unless you're in a physics lab. We say we're going to machine something, we're going to mill something, we're going to turn something. But from a physics standpoint, it's called subtractive manufacturing, because you're subtracting from a base. And the reason I bring that up is because the inverse of that is how you got the name additive manufacturing, which is displayed in this little icon right here. So let's kind of go to that and talk about laser powder bed fusion. Additive manufacturing does not do away with conventional manufacturing methods like castings or forgings or machinings. Yes, I can print a part that you normally cast, or a part that you normally forge, or a part that you normally machine. I can print it. But additive in and of itself is not going to do away with those technologies. We should think of additive manufacturing as something that complements the manufacturing floor. And at a very, very high level, this is what a manufacturing system looks like. Now, when you do a seminar or a series like this, you never really know who's in the audience. So what I want to do today is talk about this from the perspective of a very basic, and then we're going to talk to the very complex. All right, so hopefully I don't lose anybody. But you start out basically with a laser, and then that laser hits a mirror and you fuse or you weld powder. Now, when we talk about powder, it is going to be somewhere, a layer of powder is 30 to 60 micron layers thick. And what does that mean if you're a finance person or you're an accountant or a salesperson? What does that really mean? A normal red blood cell has a diameter between 6 and 8 microns. So think of it as 5 blood cells thick. A grain of sand can be anywhere from 80 microns to 150 microns, right? The thing you need to remember here is that it's very, very small. And when the laser never moves, it's the mirror that moves. And as we adjust that mirror, this laser beam moves across the build plate. Now, in a laser powder bed system, you must use a build plate. And so what this is a metal plate that is bolted on to a platform that moves up and down in the Z orientation. So what will happen is after you weld, let's say, for example, it's going to be 30 micron layer thickness, right? So this powder coater will travel across the build plate and go back, and it will deposit 30 microns of powder. We will weld a shape in that powder. And in this particular example, it's a small orange object that looks like a U, right? At the end of that, this platform will go down in the Z orientation, 30 microns, and then we do this again. All right. And we just do it over and over and over. And some parts have thousands of layers added to them. And when we say a layer, we're talking about 30 microns, and that will melt down to a thickness of about 10 microns. So you just constantly are rebuilding, relayering this part until you get it built. So to just reiterate one last time how the term additive manufacturing evolved is that when you machine something, you are subtracting material. When you print something, you are adding material. And thus, you got the name additive manufacturing. That's how that all came about. Now, I told you that this technology came to North America roughly in the area of about 2008 to Cincinnati, Ohio, by a company called Morris Technologies. Greg Morris brought this technology over using a company that was a competitor to ours called EOS. And the Germans referred to this as direct metal laser sintering. And I always thought that it was the German English translation that messed up here. Sintering is something you do in a furnace as a form of heat treating, right? What we're doing is welding. What we're doing is fusing metal together. So it should have been called DMLF or DMLW, right? Sintering is not welding. Sintering is a heat treat term, but whatever. It is what it is, and this technology has had that nomenclature for well over 15 years. In Europe, they refer to this technology as additive laser melting, or ALM, because you literally are melting the material. Sometimes it's called ALM, laser additive layer melting, or additive layer manufacturing. There are some aerospace companies that refer to it as digital manufacturing, but this became a real confusing part in the global industry, and we had to have standards. And so the ASTMs of the world, the American Welding Societies, they came on and agreed to a term to describe this technology, and that is referred to as laser powder fusion technology. That is what the industry accepts this to be. Now, in the world of additive manufacturing, there are typically, the industry agrees, there are 7 different types of additive manufacturing. And we're not going to talk about 6 of these. We're only going to talk about laser powder bed fusion. But you need to know, if you're a student, that there are actually 7, and you can take classes in each of these 7 if you so chose. So we talked a little bit about the machines. We talked a little bit about the technology. Let's talk about the third element of this, and that's powder. To print anything, you have to have quality powder. And so if you look at a material data sheet, you will see something like this. And I pulled this off the internet. This is the chemistry for nickel 718. And please notice the element they call component is always measured in weight. All right, and that's very important, and I'm going to explain that to you in the next slide. All right. So, but these are the elements that make up 718. So, one of the premier powder companies is Praxair Surface Technologies, and they have a plant in Indianapolis, Indiana. And it's really fascinating to walk through these powder companies. There are a few in the United States. They're all over Europe. On a side note, for aluminum, there's only one in the United States. So all of the aluminums that the Boeings, the Lockheeds, these aerospace companies, SpaceX, Blue Origin, they all get their powder from the same place. And that would be in California. And in Canada, there are 3 aluminum companies, and that's it for all of North America. Somebody's please mute. Okay, great. So when you go to these factories, they're ready to start a melt run. They literally have buckets of elements setting to be poured into this chamber. And so you'll see a bucket of, I'm gonna go back here. You will literally see a bucket of boron, of chromium, of carbon, of aluminum, of iron, magnesium, molybdenum. There will be buckets there, and they will weigh those buckets and make sure that the percentages are accurate. All right. And they will pour all of those elements into this chamber, and they will heat that and melt it. It just becomes a big soup, right? And once it's melted, you can see these steel lines going into the top. They will open the port at the bottom and put a few hundred pounds of argon, could be nitrogen, but in 90% of the cases, it's argon. And they will push that molten metal through that orifice, through that gate. Now, around that gate are high-speed streams of argon. And when that liquid metal hits this, it will come in contact with those high streams of argon, and it essentially atomizes all of the molten metal. And that's reflected here in this chart, or in this picture titled number 4. It falls down through gravity and comes into this hopper here where they sieve it and they stratify it. So I'm going to show you another picture that's kind of more of an example, but they atomize it here, then they sieve it, and what they'll do is they'll take, after they collect it, they'll probably put 6 or 7 of these screens on a vibrator and put those atomized powder up there, and they just shake it. And the finer particles work their way through the finer screens. They inspect it, and then you get various piles of powder in different containers. All right. So what do you do with all that powder? Well, some powder goes into binder jet additive manufacturing technology. Some powder on the higher end is used in electron beam, and some powder, the biggest particles of powder, is used in what we call DED, direct energy deposition. But the powder we use for laser powder bed is roughly on the high side 53 microns and on the low side 11 microns. Now, remember what I said, a red blood cell is between 6 and 8 microns in size. So this is really, really fine powder. You can do a lot with it, but it also provides a danger to the customer. So personal protective equipment is very, very critical. If you look at North America, here is a typical, these are the companies that I've worked with, the Carpenters, the Praxairs, the Starks, Metco, and they're located across the 50 states, really the 48 states. And here are the different the nickel alloys. Typically, if a company will do 718, they'll do other nickel alloys like 625 or Haynes alloys. Then you got the cobalt alloys, the stainless steel alloys, the titaniums, and the aluminums. It's important to remember that a company that does aluminum typically will not do stainless steel or in nickel. And it's the same. If you do nickel, you're not going to do aluminum, right? Some companies will do nickel and titanium, but that's but not always, right? If you look at the whole global market, these at the top, I have in here Germany, Canada, North America, United States, and then England. There's a lot in England. There's a lot in Japan, and then different alloys that they make, right? So there is a global market, and in all honesty, I don't have a solid understanding of the additive powder manufacturing in China. I know it's there. I just don't know it. There's 1 or 2 companies in India. I think there's 1 or 2 companies in Australia, but by far Europe and the United States, that industry. And that's because of the aviation business. So if you look at a total consumption of powder, this is where we are in 2020, roughly 3 million kilograms of powder a year is consumed. Now, you can get 10 charts from 10 different consultants, and they're all going to be different, right? Don't worry about these numbers. What you should focus on when you see a chart like this is the trend. And the trend is additive manufacturing technology is growing in the aerospace, medical, and automotive worlds at a very, very high pace. It's growing extremely fast. So let's talk a little bit about why you should print something. Just because you can print something does not mean you should print it. Each that you print will have its own business case, its own economic justification. And you have to look at the entire value chain of your decision. And I want you to think about working capital and not unit cost. And when you tell engineers that last one, their eyes glaze over, right? So let's get into this, right? So Aviation Week came out with an article on August 19th that Honeywell marked an additive engine milestone. And what this is a bearing hub, bearing in the bottom, a bearing in the top. And this general area is an oil sump. Now, why would Honeywell print that? The annual volume of that part is 2 parts per year. That particular engine was designed in 1959 and 1960. And that creates a problem. And if you look at industries around the world that have old components on them, old designs, this is a major, major problem. And they fall under the category called low volume, high value components. A foundry plant manager does not want to see a part like this. They are paid, their goal is to get out so many tons of molten casted metal a week and a year, right? They're not paid to solve engineering or supply chain problems. They're paid to print, or they're paid to melt metal and make castings. That's what they do. And so when you go to a foundry and you tell them you want one part, they're probably going to just say, we're not quoting it, right? If you find a small foundry that will do it, realize that the tools to make that part are going to start in the $300,000 range, right? Then they're going to probably charge you $300,000 to go make that $500 casting. This opens up the door for additive manufacturing because you now can print that part. It won't be $500, but you can print it for $5,000. But remember, you got an aircraft sitting on the ground waiting for a part. Without that part, you don't ship that engine. Without that engine, that plane doesn't fly. So then you have to look at not unit cost, but total cost. You have to look at working capital. Will your customer fine you so many $1,000s a day because their plane isn't flying? Whose fault is that? That is what I mean when I talk about total cost or working capital, because somebody has to pay that $10,000 a day. And after a month, that's $300,000. Somebody has to pay that. So yes, it's a $500 part if you looked it up in SAP. On the other side of the coin, there's an cost of not shipping it. You cannot tell your customer, I don't want to make this part. So another reason you might want to print deals with topology optimization. Here's a bracket that is SLM made with titanium. And see, what we did here is that we went and put holes throughout it, and yet it still has the structural integrity to meet the needs of the design. Here is a rocket nozzle, and instead of casting a solid wall, what we have done down here is we've printed a mesh, right? And you do that to reduce the weight of that component. There is only one way in the world to make that part, and that is with additive manufacturing. So if this were a casting, this wall would be completely solid. But you see the solid wall on the outside? We cut that off so you could take a look at what we have here, right? That is a rocket nozzle, but it's a very lightweight rocket nozzle. Here is a hinge for a door that we were able to print and reduce the weight. So let's talk about why a company would not use additive manufacturing. And this is what I started a couple months ago, and I'm going to report out to some federal agencies next month. And the program is called the Transfer of Knowledge and the Building of Confidence. Culture and the perception of risk are the greatest hurdles to keeping additive from being integrated into aerospace designs. So when Ford Motor Car Company in Detroit used to have hanging in their cafeteria a banner that says culture eats strategy for breakfast. And what Ford was trying to convey in that message is that regardless of the technology, regardless of how great you have designed something, the culture you work in and political risk can prevent you from being successful. Organizations that are not familiar with additive technologies can be hesitant of using it, because if you are in production with a sheet metal component and you change it, you have induced, from a theoretical standpoint, some element of risk. Now, it may be a minimal risk, right? But when you change something, you've induced risk. And when you change something to a technology like additive that industry may view as new, being new as or novel, then the perception of risk is present, and the resistance to implement this new technology, even if it saves weight, even if it saves cost, even if it removes supply chain problems, it is viewed as risk. There will be people who resist it. And what we have to do in the additive world is use the science of, we have to use material science to prove that the mechanical properties are as good or better than conventional manufacturing methods. And that's what we are doing right now. That is what I am doing, working with universities in North America. So let me try to help you with that. So let's say you own an aerospace company and you're concerned about the risk associated with additive manufacturing. Well, one of the things you want to know is, if I print something today on this machine, will it produce the same mechanical properties today as it did a month ago or a month from now? And so the repeatability of that particular machine has to be proven. You have to look at the whole value chain. And the way you do that is we use a technique called process failure mode effects analysis, right? You have to fix everything. How you manufacture your powder, how you buy your powder, how you store your powder, how you load powder in the machine. It has to be the same each and every time. The process machine values, parameters can never change. They have to be locked down. There has to be powder specifications. And that's one of the things that industry is just now catching up with. And then you have to create this material property base. And we're going to talk a little bit about that coming up. Now, there are standards out there, AS 9100, ISO 9001, MMPDS, fixed processes. All of these things have to be recognized and applied to. All right. So how do we create a material database? It is the requirements of the component that dictate the tests that you do. So the tests that I am most familiar with are tensile, machine specimens, tensile machine specimens in the vertical orientation and in the horizontal orientation. So if for an alloy like 718, you don't see that really, it's minute and sometimes not even at all. A variation in tensile properties related from vertical to horizontal. But alloys like 738 or 247, the variation can be quite large. So you have to know where that is. LCF specimens, HCF specimens, creep. All of these things have to be understood. And now you don't necessarily have to do them all for each part, but each database must have all of this data so that you can do families of parts. Okay, so now we're going to talk about A basis, B basis. B basis is defined as 100 specimens that are statistically significantly grouped together. And I'll be honest, as I've been in multiple meetings and very rarely do you ever see people agreeing on what that means. Almost always we have to print and test 300 specimens across 10 powder lots. And I'll show you an example of that. LCF, HCF, machined and as built, creep, etc. All of this data has to be generated, and that creates a real problem because it's extremely expensive. You do it to a standard, and the standard for tensile that I use, ASTM specimen E8. So you print a specimen that is basically 60,000 square or diameter, and they're 3 inches long. And out of that, you can machine an E8 standard. And to get the exact dimensions of an E8 standard, you're going to have to get that off of ASTM. I'm not going to give that to you here. So how do we do that? So here's a SLM 280 layout. And it's basically going to be 280 millimeters cubed in each direction. So here you have 100 vertical specimens, and of those vertical specimens, an E8, you can get 3 E8 specimens out of each vertical column. So if you got 100, you basically have 300 test specimens. Now this red section is where you would use 2 lasers to print these specimens instead of 1 laser. And so what your customers are going to want, what industry wants to know is, does a specimen built with 1 laser have the exact same mechanical properties as a specimen built with 2 lasers? That's the test that we are using, that we are going through now. And we are printing hundreds of these types of specimens for various customers in the United States that eventually will be given to NASA and ASTM so that they can write for industry to use. And this is something SLM has committed themselves to doing at no cost to ASTM and to NASA. And we are donating this information as long as those organizations can guarantee that it will be given to American industry. Now, here is a larger bill plate. So, and we're going to talk a little bit about this because you have 4 zones. You have 1 laser, 2 laser, 3 laser, 4 laser. So what the FAA, what our customers want to know is, will the mechanical properties of specimens built on laser number 1 be equivalent to specimens built with laser number 2, number 3, and number 4? And then they want to know, do the overlapped areas of 1 and 2 equal the overlapped areas of 2 and 3 and 3 and 4? All of that has to be tested. For a room temperature test, on Tensile, it's roughly $100 to $130 per test, right? So if you have 300 specimens, you're looking at $30,000. If you're looking at a LCF test, it's about $3,000 per specimen. So now you're looking at $300,000. That's why this is so expensive. And if you do here, you're going to have about 1,000 specimens, right? So now to qualify this, to do these tests, you're going to plan, you should plan on spending $500,000 to $800,000. And then you have to employ people to look at the data and interpret the data. So that number is going to double, really. You're not going to qualify an alloy without spending $1.5 million. Now, one of the things you have to do, particularly on a powder reuse study, is capture the powder. And so what we do is we print specimens like this. And really what these are little vessels. So when you get powder, you take 100 grams, you send it out to an outside lab, and you validate the chemistry of that powder is identical to the material data sheet. You don't want to start if it's not identical, right? And then you start printing, and you capture powder at the bottom, and you capture powder at the middle, and then at the top. So what you do here is that you measure, you send these powder specimens out to the exact same lab, or different lab, I guess, if you wanted, and you measure the chemistry as it goes up in the build. You also measure, you take one specimen, at least one specimen, and you measure the chemistry of the printed part. And what you want to know is, does the printed specimen chemistry change during the printing process? That's one build, and that's very expensive to do, but it has to be done. Then you take that powder out of there, you sieve it, you put it back in, and you do the exact same thing again. And what you have to determine, what the FAA wants to know is, does the chemistry of the powder change the more times you use it? And if the chemistry of the powder does change, not saying it does, but you do have to prove that it doesn't. But if it does change, does it influence the mechanical properties of the part you just printed? That is part of the $1.5 million that you're going to have to spend. Now, SLM has their SLM 500, that's what this is. This is 4 lasers working together. And what we're doing here is we are building small cubes, 10 by 10 by 10 millimeters. And those cubes are in sections.
Don, we are having some problems with your audio. At least I can't hear you.
Okay. So you saw the 4 lasers, right? And so this is the SLM machine that this is our platform for the SLM 500 and the SLM 800. And what we're doing in these small cubes is we're building 10 by 10 millimeters cubed, little 10 by 10 millimeter cubes, and we will take these into the lab and we will look at density or lack of porosity. And then we're building these horizontal tensile specimens. And then depending on the height of this larger cube, you can cut 1 or 2 or 3 specimens out of that. And so what this test is trying to show is what we're trying to show here is the result, the mechanical property results of this laser, laser 3 to laser 4. That's what we're doing here. So Typically, to do an MMPDS, you have to buy 10 different powder lots. All right, so I set this up for Ti 6.4 material. You're going to test in these 10 lots 170 vertical specimens. So as I said before, a room temperature test is roughly $110. So there's $5,000. And as you go up in temperature, you go up in price because there's a dwell time to get the part to 1300 degrees Fahrenheit. Typically, you're not going to go much hotter than that for titanium. You could, for nickel, this could go all the way up to 1900 degrees, depending on the alloy of the nickel. So you're going to do 170, then you're going to do 130 horizontals, and that'll give you your 300 tensile. Then you repeat that for LCF, and you repeat that for HCF, you repeat that for creep. So it's not cheap. Right? It is not cheap to do. Now, as we come up on our 45 minutes, I'm going to be real quick here. Where do students, what should they be majoring in? How can they get jobs in this technology? Let's be realistic here. We are welding. We might be welding on a microscopic level, and that laser beam is 80 microns in diameter, but you are welding. And so this is a great opportunity for welding engineering. But the problem is there's only 3 or 4 schools in America that have welding engineering degrees. Metallurgy is critical. Additive manufacturing engineering, majoring in those 2. Structural engineering, stress engineering. One of the things that aerospace companies want to know is, do these parts pose a risk if I use them? And that's where the M&PE groups, the testing, all come into play. I'm working with 2 different universities right now, and with University of Arizona, and ASU is actually going to print a paper later this year on some of the work we've done in that area. Now, at ASU, we only did tensile, I believe. But with U of A, we're going to do various other tests. Stress engineering, quality engineering. How do you inspect the quality of a part? Typically, you would inspect 2 or 3 parts and bolt them together. But with additive, you print them as one part. So how do you know part is a good part if it's inside part number 2? That comes up in the science of CT scanning and measuring parts. It's particularly in the medical field. What they're doing is they'll do a CT scan of a hip or a knee or a knuckle or maybe a jawbone, and then digitize that scan into an STL, take it out and print it. Sometimes the patient's name is printed on the part so the doctor doesn't screw it up. And so quality engineering is critical there. Supply chain engineering, supply chain management is a very important element of additive manufacturing, because one of the key benefits of this technology is to remove supply chain disruptions. Now, I've taken it all the way to the end. So this, I think I'm supposed to let people ask questions. So go ahead. This is the end of the presentation, unless I have other slides, but we're going to stop here and do questions and answers.
Great. Thanks a lot, Don. This was great. I think there's lots of very important information, especially for the students. So we'll open. Ankit, do you have anything to add?
I'll actually ask my questions towards the end. Before let's let the students ask first.
Okay. Please unmute yourself, introduce yourself, ask the question, and then you can mute yourself. Students, go ahead.
Hello, Donald.
Yeah.
My name is William, and I am actually Kids Research Group. And I have a question based on the sort of in the context of the microstructure that you would get from this method. So my assumption is that the grain size and the orientation would be biased in the XY plane since you are manufacturing this in layers. Is this largely ignored through like topology optimization and all of the rigorous mechanical testing that you guys do? Or do you guys have people dedicated to actually optimizing the microstructure as well?
Okay, so you asked several questions. All right, so let's, yes, there are people dedicated to the optimization of microstructure. So let's kind of talk about this. All right, so if you were to do a casting, the microstructure would be of a equiax type orientation, right? And then for some companies, that's good enough. If you were to imagine, I'm going to try to explain this to you, but imagine a graph on your computer where the top graph you have 718 forged product tensile results at room temperature up to 1,000 degrees. And on that graph, you have plus or minus 3 sigma. And at the bottom of the graph, you have cast 718, plus or minus 3 sigma. If you were to chart a printed specimen, the results of a printed specimen, you would find that they would fall just under or right into the minus 3 sigma of a forged product. It is far superior to a casting because with the casting, it's molten and it cools down at a very slow rate. A casting can take 30 minutes or more, depending on the mass, to cool down. And that cooling period causes an elongation of the crystalline structure. Now, with a printed part, it cools, it's solid at a rate typically around minus 10 to the 6th. All right, so it is extremely fast. Rapid cooling is where it gets its strength. It also can hurt you with other alloys, but for nickel, it's where it gets its strength. So I have visited aerospace companies in Europe that say, we're going to stress relieve these parts, we're going to machine them, and they're good enough. And they have empirical data to say that works, right? And aviation authorities around the world have looked at that data and they say, okay, great, we agree, you can do that. In North America, you typically have companies that they want a hip, right? Do you know what hipping is?
I'm not familiar.
Okay, so hot isostatic pressing.
Okay.
Right, so you take it up to 16, 1700 degrees and you pressurize it under argon to 15,000 psi. And then you do a solution in an age. Then, so when you do these things, the crystalline structure and the crystalline orientation changes, right? So the answer to your question is, we could talk all day on this, right? Because some people want to evolve into a directionally solidified part, which you can do through a linear furnace. But yes, there are people that focus on crystalline structure, but remember, everything you get off a printed part is always equiax, always equiax.
Okay.
Right? Always. But what you do with it after you print it could change it to a more DS type structure.
Okay.
All right.
Okay.
Okay.
Thank you.
You're welcome.
So Don, lots of students contacted me. They said they had a class at 12, but because this is being recorded, I will ask some of the questions that they posted.
Okay.
One or they sent me one question is like if they want to tailor their coursework, how would they? I mean, what industries other than aerospace should they look for opportunities for internships?
Oh, for internships.
Yeah, this person asked for internships, but I mean, it could just be jobs.
First is a job, then you want an internship.
Yeah.
Yeah. So, material science, you cannot go wrong with material science. If you want to actually work on the floor and design and print, you need to have a good background in CAD software. Without that, you're not going to get a job printing and designing, because everything is digital. Everything is digital. And what makes this so unique is that a lot of college students come in, they're really good at computers, and this is great, and they fit right in. I kind of remember when I got out of Purdue, I took all these drafting classes on I had a T-square, I had my own T-square, I had a drafting table, and today they don't even teach that, right? I'm not sure some of these students know how to read a print very well, but they are experts at doing CAD software and converting CAD files into machine language and printing these parts. So I would say if you want to work on the floor, you need to have a strong CAD background. If you want to work in the science and the testing, metallurgy is critical. And I've hired 2 metallurgists to work on the floor, and they learn the CAD. They can do it. It's possible, but it's tougher to go have a good CAD person and learn metallurgy. That's a science in and of itself. But both are very, very important.
Okay, great. Any other questions? I just paraphrased a bunch of questions that I put them together as one single question. So,
Okay.
the irony is that lots of the students actually have a course on metal additive right at 12 p.m. and lots of them actually left.
Okay.
There's another. Yeah, guys, feel free to ask some questions. I see some questions on the chat.
Can I ask, Professor?
Yeah, go introduce yourself and go ahead.
Hi, sir. I'm Ankita Roy. I'm actually a metallurgy student, and I completely understand the differences with the conventional metallurgy which we had studied. So, one of the questions you have already answered, that this is not. I was expecting. How would you expect a directional solidification in this? So, your answer to this is we are not getting a directional solidification, right?
So there are technologies being developed to try and do that, but you can only do that through a very hot build plate area. The other way to do that is that you take a part and you adhere it to a large mass, and you heat that mass up through and send it through a linear furnace. And once that large hot mass is hot, it will reorient the grain structure of the part that it's attached to. That's an old trick that's been around industry for years and years. The holy grail would be that nobody knows how to do is, can you print a single crystal? That's okay. Whoever does that, you will change industry. Whoever does that.
Oh. Okay.
Yeah. That's a great PhD project, but just realize you may fail.
And my next one of my next question was, when we were doing this casting process, one of the main hurdle was a challenge to like keep the mold intact wherever we are doing the casting. So here, are you associated with like breaking the mold altogether?
Okay, so you're talking about sand castings, right?
Yeah.
Right. Yeah.
Sand
Okay.
or investment where
Yeah,
we
investment.
styrofoam where we melted the mold,
Right.
but we always end up losing the mold.
Because the sand breaks.
Yeah, and everywhere we have to melt the invest styrofoams, or
Yeah.
anywhere we cannot, other than wooden frame, wooden cast, we cannot preserve the cast. So
Right.
how do you deal with that here?
All right. So, okay. So that's a casting class, and that's an investment printed. You can print a mold. Today we're talking about laser powder bed fusion of metal, but your gates and risers are probably wrong, and your wall thickness on your sand is probably inadequate. But that's kind of outside the scope of this presentation. But if you send me an email, I can give you some thoughts on that.
Okay, thanks.
Okay, sure.
And this is Rahul, you're next. But before that, feel free to please reach out to Don whenever. He's probably the best guy for us to guide us on AM. So any questions, as long as it's okay with Don, feel free to reach out to him.
Yeah. Yeah, it's fine.
Rahul,
Hi,
you-
this is Rahul. I'm a PhD student currently with Dr. Ankit.
Okay.
I have some background in plasma transfer arc, and I'm currently working on phase field. So um, we've, from my earlier experiences, we had a lot of issues with trying to deal with aluminum from a powder standpoint.
Yes, that's right.
So, I mean, so some of the methods used from welding are, pulse DC and AC. So the first question is, how does SLM deal with this? Because I don't I don't I'm not sure if you have different modes such as you would in welding. And second, what do you do about the impurities? Because as opposed to titanium or say steel, the impurities would just float on top, and whereas here, this is a much harder issue.
Yeah.
And third, how do you deal with a powder feed as opposed to a powder bed?
Right. Okay. A lot of questions there, and you can talk all day long. All right. So, you're at University of Arizona, right?
I'm at ASU.
Okay. Oh, at ASU. Okay. All right. Okay. So I'm not going to tell you how to answer that because there's an expert in this field of aluminum named Dr. Andrew Westerman who teaches at U of A. And I was going to say, well, walk down to his cubicle and talk to him. Send me an email. You asked me about 5 questions, and I don't have a good answer for you right now. I view aluminum as the devil's favorite alloy.
Sure.
It is so hard to deal with, and it doesn't take much to make it so and impure enough where you can't do anything with it. And send me an email. Do you know Professor Drev?
Bhatti?
Yeah. He has my contact information. Send me an email
Sure.
or connect with me on LinkedIn, and we'll address this on a side table. Okay.
Yeah, great. Thank you.
All right. Thank you for asking. Good luck on your dissertation.
Sure. Thanks.
Any other questions, folks? Because we are getting close to the finish line, so maybe 1 or 2 more. And again, feel free to reach out to Don as and when you can. Ankit, do you have any questions?
Yes, I do. Don, you showed one of these specimens that you have printed at SLM, which has got these 3 vessels joined end to end.
Yes, that's common. Yep.
Yeah. And you did mention about the chemistry test that you guys do by taking samples at different cross sections. So,
That's
you know,
right.
I'm a metallurgist by education. So I have to ask this, that do you also care about the microstructure? And if you do, then what's the metric you follow to compare these microstructures?
Okay, so in a powder, the answer is yes, right? The answer is yes. So typically what we would do is that the metallurgist in the company would agree on what microstructure they want for a particular component. All right. So that may mean you take an, you heat treat it in such a way to give it certain properties. That's metallurgy 101. Right. That's it. So it is the metallurgist and the design engineers that tell me what it is I have to print and meet. They give me the requirements. Now, when you are doing this test, what we are looking for are deltas. So we take, as I said, you take the powder from the virgin material right out of the can, and you send it off to a lab to be tested, and to ensure that the elements are there at the correct percentage, right? And then what you do is you open up those vessels that you're referencing, and what you want to know is, did the chemistry of the powder inside those vessels change during the welding process? And it could change because remember, you're welding, so you're creating soot, you're creating carbon, right? It is possible that some element of carbon fell into that vessel and then changed the chemistry. Now, if it did not change, that's great. But if it did change, you want to know how, right? So you also, right next to that, you have a printed cylinder all the way up, and you measure the chemistry of the printed cylinder because you want to know, did any elements evaporate away under that laser that now takes that material out of spec, right? Now, if it did, if it didn't, everybody's golden. Let's go celebrate. But if it did the change in chemistry influence the mechanical property results? That's what you want to know. So at the first 75 millimeters is one set of bars. The next 75 millimeters is another bars, and the next 75 is another set of bars. And what you want to know is, did the mechanical properties of the top layer differ from the mechanical properties of the second or the first layer? That's what you want to know. And so they want to know that over time, over consistency. So you take the powder out, sieve it, put it back in, do it again. And it's a big test because when we did the 718 powder reuse study, we did it 20 times. That means 3.5 months of welding nonstop. It's expensive, it's time consuming, but what a science project.
Yeah, it is. All right, thank you. Thanks for your answer, and a great presentation, by the way.
Well, thank you. So I will give this presentation to Krishna, and then he can circulate it however he so chooses.
Sure. Don, there are 2 more questions if you have the time.
I have the time for you. Please ask.
Okay. So, Nicholas, you go ahead, and after you're done, Monica will ask the question. Nick.
All right. Hi, Donald. I'm an undergrad in material science, and I work with Krishna for the heated fill plate project. So we were dealing with actually Inconel 718, and I think you kind of answered Ankit kind of similar question. It was more towards seeing the quality control, and could you reiterate when you were talking about repeating the process 20 times? Is that kind of reusing the powder, or is this a fresh set of powder within the same size?
Okay, that's a good question. That's an excellent question, right? So to meet the MMPDS standards that were established by Battelle Institute, they want to see 10 different lots of powder, right? Now, that can be interpreted different ways. The true pure way is you go to 10 different companies and you get 10 different powder lots, 10 different powder heats, and you test each and every one. And what's so good about that is that you can look at 10 different companies and see the quality of their product base compared to a baseline. Right now, the other element is that you may want to go to one company and get 3 different powders to see if you have consistency within that same company. All right, so that takes care of that. Now, when we're talking about a powder reuse study, it is one powder. Somebody has to mute themselves, I think. Right? It is one powder lot used over and over and over and over, and you are not allowed at any time to add virgin powder to the lot. What you want to know is, do we see a material degradation over time? And if we do, that's if we do, where does it start? And how do you, and so I know for 718 we didn't see that, right? Over any, so you can use it 20 times. You could probably use it 30 times. We just never tested over 20. So the question is, let's pick an alloy. Let's just say theoretically we're going to pick ALSI 10 MG. All right. Let's say we see a degradation at powder reuse number 7, right? You have an option. You can say in your process specification, after 7 times, you throw the powder away. Or after 7 times, you put an equal amount of virgin powder in it, and you're allowed to use it 4 more times, right? So you have that. There are options there. But whatever you decide to do, you have to prove it with empirical data, with science. You can't just go make this stuff up. You have to prove it and put the data on the table. It is what I call objective evidence of compliance. You have to put the science on the table and you have to do the test. Otherwise, you throw it away. Right? So did that answer your question, I hope?
Oh yeah, it kind of answered like the first half of it. I think I might be taking too much time. I might maybe send an email over.
Yeah, I can give you Don's email ID and you can communicate with them. I think we have 2 more minutes left, and Monica is next. Monica.
Yeah, thank you, Professor. Hi, Donald. I'm Monica from a master's. I'm a master's student from Material Science and Engineering. So I have a general question for you. I would like to know your opinion regarding the growth potential of 3D printing in semiconductor industry, especially using directing writing. Can we produce conductive inks, and what is the potential of that field?
The 3D printing of electronics is a technology that is beginning to emerge, and there are companies in California really leading the way. I have not been in that field because I always did aerospace parts, right? But the 3D printing of electronics is a major economic opportunity for industry on a global basis. Please think of it like this, right? There are thousands of jets, military jets around the world that were introduced in using computers with 386 processors, right? And the B-52 is 70 years old, right? Air forces around the world have these circuit cards, these circuit boards that they're never going to be high volume. And that's why Intel and AMD are never going to go solve this problem because they're not going to put billions of dollars to go make 200 chips. They're just not going to do that. So 3D printing offers an opportunity for you to manufacture a chip that this falls under what we call very low volume, very high margin, right? If you can figure out a way to solve this problem for this industry, you become the next gazillionaire. But 3D printing of electronics is just now beginning to emerge, and it's growing. There's a company next to Sandia National Labs in New Mexico. The name of them escapes me right now, but they are printing electronic schematics on surfaces and trying to connect them with sensors of components. So it's growing, it's out there, it's just not as predominant as laser powder bed is. You do some research, you can find those names. But it's out there, it's growing, it'll be there to answer your question.
I think the name of the company is Optimec.
It is Optimec, that's right. They're a spin-off of Sandia.
Yes. So Monica, if you are interested, you can reach out to them and we can put you in touch with them if needed, if you're interested.
Sure, Professor. Thank you so much. I would like to go with that.
Yeah. Okay. Anyone else? I think, Don, I think we overshot the time. It's 12:15 already. So let's call it a day. Thanks once again for your time. This was incredible, especially for the students, because they really now get where this field is headed to with the job opportunities, which is exactly where, I mean, that's what we want to be the outcome of these talks, right? To really inform the students and keep them abreast of what's going on. As faculty, we have lots of questions to, how to engage, how to teach, how to, the state of the art. How do we make sure that the students are exposed to the state of the art? But that's a conversation, ongoing conversation we can have with our respective school administrators and how to push this really incredible field of additive manufacturing and make sure that the students are all getting educated on the state of the art, and they are ahead of the curve in some sense. And that's
they are. Yeah.
Also, it's completely our fault, but we have a MateriAlZ logo polo that we want to ship out to all our speakers, and we've been too lazy because of COVID. No one wants to go to the post office, I assume, but at some point,
as soon as COVID's over, I'll just drive down. You're only a few minutes away, right? It's my house is almost between the two schools, ASU and U of A. So I'll come down there and meet with Andrew and talk to you guys, maybe talk to a class, and you can give it to me then.
Yeah, sure. But we will probably ship it to you soon, and we would like you to take a selfie of you and the T-shirt or the polo.
Yeah, we can post it on the website.
Yes. Okay, so I think let's call it a day, and thanks a lot. And once again, on behalf of Ankit, Christina, and Erica, we would like to thank the speaker as well as the audience. I think we had 75 people log in today, which is higher than the last two times, but that's great. I think it's a great way of disseminating information to everyone. We had people calling from Carnegie Mellon to the Army Research Labs.
Yeah.
We had folks from Army Research Labs call in and other places around the US. I also saw some folks probably from outside the US, but I can't confirm it at this point. But this is great. So thanks once again, Don, for an incredible talk.
Yeah. Well, you're most welcome, and you know how to get a hold of me when you need to. Okay.
Definitely. Thanks a lot.
All right. Bye-bye. Have a great day.
Bye.
Good weekend.
Yep. You too. Bye.